Good morning. Good morning, ladies and gentlemen. You're welcome. You're welcome. Glad you all could come. Great to see you all. Let's make a start. First of all, I'm Michael Stack. I'm secretary for the program committee, and on behalf of the program committee, we'd like to thank our sponsors. Here they are up here. In particular, our gracious host, Google. Google was kind of cool. They made it so that if you sponsored HBaseCon, the money actually went straight to the Apache Foundation, which is very nice of them. Thank you, Google. In particular, thank you, Google, for giving us Justin Kesslin. The man took care of all the logistics, everything from last-minute sign-ups to keeping the program committee on cue. Thank you, sir. Great man. Just a few things, a bit of housekeeping. As you can see, there's this room here, the next, and then there's another room in the building behind us. It'll be signboarded, but keep in mind that there's little space between talks. We have a lot of talks that are, and the talks themselves are short, and the transition is going to be super short too. We just want to keep the day full of good stuff. So keep that in mind if you're moving between buildings in particular. Lunch will be outside, as will be a little party at the end of the day. Take note of the Wi-Fi. And that's it. Have a good day. I'd like to start by introducing our chair, Mr. Andrew Purtell. If you don't mind, Andrew, you'll give a little talk on the current state of Apache HBase. Thanks, Andrew.
Thank you. Okay, so I'm the chair of the Apache HBase project. If you're not terribly familiar with Apache, really all that means is I'm the project secretary. There's certainly no leadership aspect involved with that in an Apache project. Anybody who works on the project is in a leadership role. But as secretary, I do quarterly reports on project health to the board, and I thought I would share with you. I know most of today is going to be about HBase, the technology, HBase, the use cases. But in the beginning, I think that I would like to talk just a few minutes about HBase, the project, and HBase, the community, if you'll indulge me. And so the executive summary is the project is healthy, stable, and we have excellent uptime, which are all the attributes that you'd like to see in a large-scale database deployment. And by uptime, I mean we might be fudging the lines just a little bit, but back in 2007, the HBase project was incepted as a sub-project of the Hadoop project. Didn't become its own top-level project at Apache until 2010. But I think it's close enough to call it the 10-year anniversary of the Apache HBase project. So happy 10th year birthday, Apache HBase. Which I'm unfamiliar on the sourcing of. There's also an apocryphal saying that it takes about 10 years for a database to become stable. And so that means maybe we're approaching that line finally. So this will be brief, I promise. Just want to talk a little bit about what makes up an Apache project, and that's the contributors who write the code and send them our way, like, please take our code. And then there's the committers who are like, hey, we're really happy to receive your code and give it a good looking over, and maybe we'll commit it. And finally, what's known as the project management committee, which sort of looks at the project at a meta level and tries to decide how things can go most smoothly. So for comparison, right now, HBase has, over its lifetime, had 163 contributors. A more boutique, tightly focused project like Zookeeper would have 34. Projects that are closer to HBase in scope and scale and community composition, Hadoop and Hive, I think we're right in there, right in this middle pack. And I also list Apache Spark, which is the outlier for the Apache Foundation at this point, with 919 individual contributors. So we'll never get to that point. it's unlikely that any other Apache project in any near time frame is ever going to get to that point. But the takeaway is that we're very comfortably in sort of this middle tier. And if we have just 10 more contributors, we'd be right there with Spark. 11, we've got one, sorry, with Hive. If we have 11, we'll have one more than Hive. So if there are 11 of you in this room who have never thought about contributing to Apache HBase yet, but would like to do something, and when we take all patches, documentation patches, single line patches, whatever you like, step up, contribute, get us across the line, all right? And I'll take that back to the Hive guys and be like, So since HBaseCon last year, we are now at 60 committers. We've added 8. Our PMC has grown by 7. In Apache scale, these are healthy numbers. So, since the last ApacheCon, we've also produced 16 releases on 4 code lines. A special note about the 98 code line, it's dead as of January of this year. I was the RM for 98, and please let me, as the RM of 98, impress upon you if you are using any version of HBase 98 or 96 or 94. You really need to upgrade. We've all moved on. It's all 1.0 plus. We're officially a Samver project. These old code lines, it's strictly of historical interest at this point. You can continue to use them. You'll be on your own if you use them, is what I'm suggesting. And although I will say that because it's an Apache project, if you would like, if there are a number of you who are on 98 and would like to band together and make another release of 98 to fix some problems that you are having, this is always something that you as a community can do, and we will definitely facilitate that. Okay, so just because the RM or the PMC has said 98 is dead doesn't mean that you the users have to go along with this plan. That's the nice thing about an Apache project. But if you don't want to take on that effort, and I recommend that you don't, I would strongly suggest you think about upgrading. Okay, our current stable branch is 1.3. We've only had 2 releases from that branch. It's relatively new, but we're all really interested in that branch. I am at my workplace. I've got colleagues at Facebook who have been running it for a while. It looks like some of our colleagues in China are also really getting into it. So it looks like the leading edge of stable HBase in production is going to be 1.3. So if you're looking for an upgrade target, that's probably it. I'd like to talk a little bit about Jira as a rough measure of our velocity in this slide, and then we'll talk about commits. So I report on a quarterly basis numbers including how many tickets in our tracking system, the Apache Jira, are open and closed. And I would like to say that we've declined a little bit in this year. We sort of peaked around the end of 2016, early 2017. As you may know, we have a huge major release 2.0 waiting in the wings. And we had, towards the end of last year, early beginning of this year, a lot of work coming in to the finish line for 2.0. Since then, our velocity is down a little bit, but these are the stabilization issues, the debugging issues, the things that take longer to fix. So these earlier issues were like, here's a feature thing, get it in. Here's the other phase of the feature thing, get it in. Well, we're past all of that. So although we're taking on fewer tickets, they have more meat and are the interesting stabilization work that happen out just ahead of a new major release. So also I would say still indication of good project health. Commits, we are on track year over year, and you can also see what I was talking about reflected in the commits somewhere in the in the October, November, December range, right? Where a lot of things have started landing for 2.0. But the takeaway here is if we use the commits as a proxy for project health, we are stable year over year. Okay. So coming up, I would be remiss not to highlight all of the notable improvements in 2.0. We just branched this past week for release 2.0.0. Stabilization now begins in earnest. 2.0 contains so many things. I have a hard time even coming up with the list. So, thankfully I can save myself by looking at my slides. So there's the assignment manager version 2 based on the procedure version 2 framework. Something called accordion, which is a fantastic in-memory compaction enhancement, and many other goodies like a real asynchronous client, first-class asynchronous client, a new RPC server built on Netty, group-based assignment, the off-heaping of the read and write I/O paths, significant improvements to the coprocessor API where we do more hiding behind opaque types to make the authoring of the writing of coprocessor environments more stable from an API perspective, and so many more. So in this program, you'll find half the material you'll encounter today is the goodies that are coming up in 2.0. And if that's something that you're interested in, you definitely want to check all of those out. Last but not least, we will also be branching for a 1.4.0 code line in the near future. And that's all I have. Thank you.
Okay, oops. This one. Hi, I'm Lars. Just wanted to give you all a brief update about where we are with HBase and Phoenix at Salesforce. And we have been working in various roles for the past 12 years. So 2 years ago, I was at a stage like this, and I showed you a slide that looked like this, right? And I would put some text in there. It's the Zookeeper bike, the HBase guy who hangs on the Zookeeper bike, the HDFS plane with its engine on fire, and the commodity hardware RAM and unstructured shrubs, right? So that's what I showed you 2 years ago, right? So where are we now, right? And so now we are using a ton of HBase and Phoenix right now. I will give you some numbers. I can't give you the latest numbers, so those are numbers as of a random time in the past, and not all from the same time. But to set the stage on this a little bit, we are big users of both relational storage like Oracle and Postgres and so on, and now we're going more and more into semi-structured data with it. And what we do store in HBase and in Phoenix is a mix of customer data. So our end users actually interact with the data directly with HBase for some of the use cases. And we store internal data in HBase as well, such as metrics. Sample of the use cases. And when I looked at the slides, I noticed I missed the most important one here. And that's the direct data storage of end user data in HBase, where they interact through the platform we give to our users directly with HBase. I don't know why I missed that one, but the rest of the use cases are we do real-time tracking of login data of our users, so we can not to record it, but to give them a warning when some weird things happening. If if one user logs in from China and from Germany, within an hour, that's physically impossible, and so we would then go and alert our users. We have a second set of use cases where we take data that is stored in our operational relational stores, and for example, audit trail history data, and we move that into HBase on a schedule. For our Facebook-like thing that we call Chatter, we store all the feeds in HBase. We also do our low latency at mention lookups from HBase and from Phoenix. And the last one is kind of boring for most of you, I think, but we have a whole branch that does marketing campaigns, and they store their data about how their campaigns are doing in HBase. And so that they use then to do reporting. They are doing what I will be doing, machine learning on it soon. As for the internal use cases, we have one. We take a stack dump of every app server we run all over Salesforce for every n minutes, and we just write the stack dump to HBase. So if anything ever goes wrong, we can look back at that time. What were all the threads running back then? And it's a huge amount of data. It's written. It's a lot of writes, not that many reads, and it's a nice use case for HBase since we find these stack dumps by their stack hash. And then the second one is we actually do record metrics from all the machines we have, all the machines we run at Salesforce, and they go all into a single HBase cluster. So with that, let's do some sizing. So we run more than 100 clusters right now. It's a lot of clusters. We're trying to actually reduce this and run fewer, bigger clusters instead. That's from a questionable early architecture choice, I would say. We do about 4 billion write requests on a given day, except for the weekends where it's lower. We write about 80 terabytes it's more or less on some days into HBase every day. And as I said, those are historical data. It's not the current data. That's about, if you think about how much this is, we actually write at 8 gigabits a second into HBase. This is sustained, right? Peaks are much higher, but it's a fairly high rate, I think. Reads are less. We do 600 million reads on a given day, roughly. It comes to about half a terabyte we read, and that's because a bunch of the use cases are heavy writes. We only read the stack dumps back when we actually have an issue. We only read the the archiving data back when users go and look at the archive data. So that brings us to the main internal use case we have, and that runs on OpenTSDB, where we write data from more than 80,000 machines right now, and it's historical numbers. I keep repeating myself here. And we have, up to this point, we have about 8.4 trillion metrics stored in a single HBase cluster. We sampled a 6-month time frame some time ago, and it came to like about almost 3 trillion metrics in 6 months. We read back these metrics, again within 6 months, about 210 billion in 6 months, and I think that's all I had. Yes. So nice and sweet. How do I go back? There. That's it. Thank you.
Thanks, Lars. As we don't have a clicker, let's just use arrow keys, right? Okay, all right. So, hi everybody, I'm Carter. I'm the lead manager for Bigtable at Google. And just wanted to thank you all again very much for coming here. It's really exciting that we can start sponsoring these events. HBaseCon, as I always mention every year, is one of my favorite conferences. It's a group of people who are very committed to open source, and I always end up having very exciting conversations and technically deep conversations here in a way that I don't get an opportunity to at most other conferences. So we're going to start doing 2 of these a year, actually. So we have this one here on the West Coast, and we will be trying to organize another one on the East Coast around the Strata again. So, okay, so let me get started. I'm going to talk a little bit about some lessons we've learned about Bigtable over the years. And you may agree with some of our conclusions, or you may not. And if you don't, feel free to come and corner me in the hallway. I would love to hear your side of things. I'm going to start with a quick kind of background on Bigtable. So this is from a park, I think, in Germany somewhere. I have this, anyways. So Bigtable, first line of code was written in 2003 by, it was 1CL submitted by Jeff Dean and Sanjay Gamawat. And it went in production in 2004, and we launched an internal service in 2006. And Bigtable was initially designed to basically store a web index, which is something we're interested in at Google. Because of its scale, it quickly got picked up by other types of projects here as well. So before you had Bigtable, the only petabyte scale system we had essentially was GFS, which was our file system, where you would store blocks. And it was not very good for random access, random reads and writes. And we had Bigtable come along, and now you could do random reads and writes. You could get petabyte scale, and this was exciting. But people wanted to develop applications on it. People who wanted to develop applications on it found the interface was a little bit clumsy. So if you want to perform arbitrary queries against the data as you're designing your application, it's not really well suited for that. You design the schemas around the way you want to query the data. And additionally, if you wanted high availability, you want to replicate the data across multiple geographic regions. And as soon as you do that, now you've got eventual consistency going on. And when you're trying to have an interactive application, you start to see between the seams sometimes where your data goes back and forwards in time with the eventual consistency. So internally, we built another layer on top of Bigtable called Megastore, and there's a paper published on this. This was written in Java. Bigtable was written in C++. And basically, it applied a layer that would handle consistency, and it was a lot like a document store. It would allow for some type of transactions among related groups, not arbitrary transactions, but a little bit more than you had before. And we threw in a Paxos layer, which allowed for there to be some consistency across geographies. And this is very important to creating an interactive experience for applications. And so a lot of the stuff that we have internally, Gmail, for instance, are built on top of this Megastore layer, so that they could write as you would normally with an interactive application. And I'll continue to stir a little bit about what's going on at Google, but I want to make a point right now that these additional layers that are being built in HBase on top of it are actually really valuable to the developer community. The interfaces of HBase are great for certain types of workloads, but sometimes people need to, write a new query or do joins and things like that. There's a lot of great. I happen to pick out 3. If your project is not on here, I'm sorry, but that's just the first 3 I put up here. But having a great SQL interface on this really does simplify HBase if you're trying to write interactive applications. And I think continuing to work on these sorts of projects is going to be important for the user community. Okay, so back to our internal story. Megastore certainly made the interface for programming easier, but the performance was not exactly what we wanted. So you had actually fairly slow performance because you have this completely separate layer in Java that's trying to interact with Bigtable and pretending it's a different sort of interaction than is actually there. And what the follow-up was to build basically what was at the time a fork of Bigtable with the transactions and with Paxos and consistency built deeply into the tablet servers themselves. And what this came out to become was Spanner. And Spanner is now our internal application database for people building new systems that need the kind of SQL interactions, they need global consistency, those sorts of things. So now you've got a few different options inside of Google. And one of the things that I was I was one of the people over the past few years as the Bigtable lead, trying to help people figure out what do you use in which case and which database do you use, and trying to create choosers and things like that for people internally. And what we did to explore this, and we've gone through kind of a few different curves, and one of the things most recently I explored was a thought exercise I call it a proof by contradiction, where I said, if we took Bigtable out of the picture, what all would start to break? And it became pretty clear pretty quickly. And I think this follows closely with what Lars was talking about at Salesforce, is the ridiculous throughput that Bigtable can achieve is unparalleled for any other kind of random read-write access database out there. And this gives it a very special type or set of use cases that is truly unique at achieving. And internally, we have branded Bigtable as our online analytics database. Now, when Stack saw this this phrase earlier, he raised his eyebrows a little bit, because analytics database is often used to refer to the columnar type stores like Impala and things like that. And it's true that while these Bigtable style databases are slower at doing large aggregate queries across all your data, that's not the only way you do analytics. The time series use cases, where you're trying to collect billions of metrics, are really important to be able to have random access to that data, being able to cut slices out of it at random portions. You don't want to run a multi-second or multi-minute aggregation query every time you want to ask questions about your data. So one of the use cases that I think is particularly interesting going forward for both us at Google, and also I think for the HBase community, is going to be the Internet of Things. This is just starting now, and it's already very big. And I think Gartner estimates the services sector of Internet of Things, which includes all of us and software and consultants and things, is going to be in the hundreds of billions of dollars. It's going to be really, people are putting sensors into everything. And a lot of these companies, manufacturers, et cetera, are starting to install them, but they don't always know what to do with it. So they're internet capable. But when you have all these devices that are going to be pouring out a bunch of information, you need the ability to drill down to individual pieces of that data. One example, there was another slide, but I didn't get it in on time. One example is I was reading about last week. There's a mine owned by the Rio Tinto Mining Corporation. It's about 2 kilometers underground, and its ambient temperature is 175 degrees Fahrenheit. And it floods with 600 gallons of water every minute. And they have to try and make it so that they can mine, and actually so that people can stay down there and not be injured or die. So they have 10,000 devices down there that are constantly reading humidity and temperature and water flow and particulate matter, and they're pumping these into they're pumping this into a system that's looking for anomalies. Now, when something starts to go wrong, they don't want to say pull out Impala and do aggregate queries and look at long trends. They want to see what's been happening with this particular sensor right now in the last 5 minutes. They want real-time data, and this real-time analytics is really the sweet spot for this sort of architecture. I'll talk about ad bidding briefly too. I know that it's not as big in HBase as it was in the past, but I don't see why that should be the case going forward. So the ad bidding systems at Google are still backed by Bigtable, and they're a really nice fit for it when you're reading. It's kind of like the Internet of Things use case, where you have millions of browsers around the internet constantly sending updates, and you're trying to get data back out to respond to bid on ads. I think Aerospike is probably becoming the dominant thing in ad bidding right now, but I don't see why HBase couldn't make a good go at it if it can get its latency down a little bit more and be competitive in that space. Then there's just colossal data projects. There's just other projects where you just kind of laugh at thinking of any other type of story you would put the data onto. You have the, I had Adhar there. I think they moved to MapR, but there's Alibaba, which runs their entire search engine on HBase. You have global messaging systems like Facebook, who did a bake-off, and they actually built Cassandra, but they run everything. They run their messaging system on HBase. And there's the line messaging system as well, which is about as big as WhatsApp, from what I understand. We did a load test a year ago to demonstrate processing for the consolidated audit trail with the SEC, which is a process to ingest and link 100 billion events. It was kind of like finding a needle in a stack of needles. And we were able to hit 33 million durable reads and writes per second. And you just can't do that with any other database out there. So that's basically it. I just want to point out, that there are some really exciting challenges coming up. And I think that HBase and the Bigtable architecture are quite uniquely suited to taking advantage of them. And I'm really looking forward to seeing what comes next. So thank you.
Good morning, I'm Phil at Xiaomi HBase team. Today, my colleague Guanghao and I will show what we did on HBase in the past year. Xiaomi is a Chinese technology company founded in 2010. It is one of the top-level smartphone makers in the world. And Xiaomi has many active users all over the world, more than 20 independent apps whose daily active user is more than 10 million. And more than smartphone, Xiaomi also has many kinds of devices like TV, router, and smart band. Since HBaseCon2016, we have 1 new PMC member, 2 new committers, and resolved more than 180 issues in the community. Today we have 5 parts to show. I will present the first 2 parts and Guanghao will show the others. We divide our scenario into 2 kinds, online services and offline computing. We use our own data centers as well as cloud services. Several years ago, we used 0.94 as our initial version. Unfortunately, 94 used Writable as his client-server communication data protocol. Since 98, we use protobuf. They are not compatible. In the last year, the community did a service to users, and it showed 19% users still use 94. So here we show some experience of upgrading from 94 to 98. At first, we have to use 2 clusters because we don't like downtime. One cluster is 94, the other is 98. And we use this Apache from this issue to support Swift replication to transfer the data. Here is a flow of transfer the application from 94 to 98. First, we add a disabled Swift replication peer to the 98 cluster and take a snapshot. And use export snapshot where MapReduce to copy the snapshot. If the HDF version is also too old, we should use WebHDFS. After copying the snapshot, we can clone the snapshot to a table in 98 and enable the Swift here to push the holding logs. The logs of the logs is maybe the number of logs may be very large if the table is large because the Excel snapshot needs some time. We should wait all logs being pushed and there is no any replication delay. And now we can restart the application from the old client to the new client. The downtime of application is only several seconds to restart all application instances. And after all of this, we can shut down the cluster and merge the machine to the 98 cluster. And after we upgrade into 98, we may upgrade to 1.4 directly because we have many features in our own branch, and they are only committed to 1.4 or higher version. So we will upgrade to 1.4. In the patch of the community, we use read server to bind a new port as a Swift server for replication. And here we separated to a independent process because we can reduce the GC of region server, and we don't need to restart the region server when we want to change the table mapping config file. There is a table mapping file because in 98 we have namespace and the table name may be not same. Another work we did is use G1 rather than CMS. When we use CMS, we have to run 4 region server instances in one machine to make use of 128 GB memory, because CMS cannot handle a large heap, and CMS cannot compact the heap. So if there are many fragments in the heap, JVM has to do a full GC, and it is a large stop the word time. G1 can collect and compact part of the heap, so we can use a very large heap, and the probability of full GC is much lower. We almost never see any full GC when we use G1. Note here we must use the latest JDK8 because the older version has some bugs. In the heavy load, the JVM may be crashed when we use G1. Here are our parameters when we use G1. Our 99% latency is sometimes impacted by the mixed GC stop the word, but we think it is acceptable because the max latency is much lower. Because there is almost no full GC when we use G1. We use replication to push data because we have many data centers. Here are some important improvements on replication in the past year. The first one is to pushing all tables in namespace. So when we create a table, we don't need to add append the table to the peer. The second one is throttling in peer level rather than region server level. Third one is to prevent outflow memory when we have many peers. The next is transfer only one log from a dead region server. This is to prevent all logs of dead region servers being transferred to only a small number of region server. The last one is push data serially, and I will show more details. Before the patch, we cannot guarantee the order of logs being pushed. For example, when a region is moved or failover to another region server, the logs written in the second region server will be pushed directly, and there is no guarantee about the order. So we may have a state in this picture, log 4 and log 5 may be pushed before the log 3. So in slave cluster, we will see a state that we can only see what log 1, 2, 4, and 5, and which is a state that in master's cluster we will never see. So after this patch, we have some logic to handle this situation. We will wait. When we want to push the former logs, we will wait all. When we want to push the log 4, we will wait all logs before it being pushed, and this will increase the delay of. This may increase the delay of replication. So it is not a default setting. We should set replication scope to 2 if we want to use this feature. And my part is over. Thank you. And now Guanghao will show the others.
Hello, everyone. My name is Guanghao, and I'm from Xiaomi HBase team. And we use HBase to provide a storage service. Today, I will share some problems what we found and some improvements what we did. The first part I will talk is about the confusing behaviors. About the replication, if one delete was pushed to the peer cluster firstly, and it was removed by major compaction, this may lead to the inconsistent results between source cluster and the peer cluster. The second case is delete mask puts, even the put that happened after the delete was entered. The last case is inconsistent result when we use the filter to read data. Suppose a table, the color family's max version is 3, then we put a 5 key value, and the T5 has the biggest timestamp. So T1 and T2 are gone from user's view. But when we scan with the value filter to read the cell whose value less or equal to 3, then we will read the T1 and T2 back again. This is really weird for user. So the reason is the execution order in scan query methods match column method. It check column first, then check by the filter. Finally, it check by versions. So because T3, T2, and T1 will pass the filter check, and they will pass to the versions check. And the max version is 3, so they will be added to the result. So our solution is to adjust the execution order. We will check versions first, and finally check by filter. So look at this case. Because T5, T4, and T3 will pass the version check, and T2 and T1 will be skipped by the version check. So they can't be passed to the filter check, and they can't be added to the result. So we will get a consistent result after this fix. The second part I will talk is about the scan improvements, what we did. We add inclusive and exclusive support for the start row and stop row. And we add a set limit method to limit the number of rows will be returned. We unify the implementation of the small scan and regular scan. In HBase, the regular scan takes at least 3 RPC curve, and only the next curve return results. But the small scan takes only 1 RPC curve and return results directly. Now, we unified them. Our scan RPC request will return results. And meanwhile, the scan support set read type now. There are 3 read types: period, streaming, and default. For the default read type, it was controlled by server. Now we use period by default, and we'll switch to streaming read if needed. The last improvement I will talk is about the row level consistency. Let's look at this case. We put column A and column B with value 1. Then we start our scan. Because the last committed write MVCC number is 1, so the scan will use read point 1 to read data. So we will read column A with value 1. Then we put column A with value 2 and delete column B. A consistent result. Or another consistent result is column A with value 2, or column B has nothing. But when region was moved to a new region server, we maybe restart the scan from the middle of a row. So the restart scan will be sent to a new region server, and we will use a new read point to read data, and we will can't read column B. So from user's view, it read column A with value 1 and read column B nothing. This is not a consistent result. So our solution is pass the read point to client. When region was moved, we use the previous read point to restart our scan. So for this case, the restart scan will use the previous read point 1, so it will read column B with value 1. This is a consistent result. But there are still has a consistency problem when there are compaction. We still use the before case. We still use the previous case. put the column A and the column B. Then we start the scan with read point 1. Then we put the column A and delete the column B. The consistent result is the same with the previous case. But the different thing is about the compaction. When the region was moved and the new region server take a major compaction for this region, then the column B will be rarely removed. So even the client restart the scan with the previous read point, it still can't read the column B. So for user, this still is not a consistent result. We open an issue for this problem, and it is still open. So any suggestion are welcomed. Our one candidate solution is disable the compaction for while when we open region. So for this case, because the column B can't be compacted, so the restart scan will get a consistent result. The last part I will talk is about the async HBase client. We implemented it by using the async protobuf stub, and we use the Java 8's completable feature directly. When we did a test for this, we found a performance issue about the GDK. So we suppose you use the latest version of GDK 8. For the user API, we have two async tables. The raw async table is for the experts, and we have an async table which uses the user's executor service to execute the returned completable feature. For scan, we have a result scanner in the old style scan, and we add a scanned result consumer which uses the observer pattern. And we did some tests for async client. We did this test by start or async get or put to get a complete feature and wait there until it complete. The latency result shows that the async client has almost the same latency with the blocking client. So welcome to use the async HBase client in HBase 2.0. Thank you. That's all I always shared today. Thanks.